Hello everybody. In this video I'm going to model how to do a gas law problem. So here's a gas law problem. First step, read the problem statement. When a sample of gas is placed in an ice bath, the volume is 345 milliliters. When the sample is moved to an oven, the volume increases to 745 milliliters. What is the temperature inside the oven? Hint, you need to know the temperature of the ice bath. Okay, so we've read the problem. The next step is to identify the given values and the unknown value. The given values, you have start with a volume of 345 milliliters. So V1, I'll call it V1 equals 345 milliliters. And when it's put, the gas sample is put in the oven, the volume increases to 745 milliliters. So I'll write that down as V2 equals 745 milliliters. Okay. The initial temperature when the gas is in the ice bath, that's the temperature of melting ice. An ice bath, it's ice and water, so T1 would be 0 degrees Celsius. 0 degrees Celsius. Okay, what is the temperature inside the oven? That's the unknown, T2 equals a question mark. Okay, now notice these first values, we call those the independent variables. Okay, those are the variables that are given in the problem statement. And then the unknown variable is called the dependent variable. Now, the dependent variable, the value of the dependent variable, it depends on the independent variables. Okay, so we have our variables. The next step is to identify a gas law that will give you the value that you're looking for of the dependent variable. So we're going to go to a table of gas laws. And what you're looking for is a gas law that involves the variables that you're using, that you have in the problem statement. In this particular problem, it's Charles' law. Charles' law depends on the volume and the temperature of a gas. It's a direct relationship, and in particular, we're looking for the law under two conditions, an initial and a final condition. Okay, so let's go back. Let's write down our gas law. V1, Charles' law, over T1 equals the final volume over the final temperature, T2. Okay, so we know everything here except for the T2. Next step is to manipulate the equation so that the dependent variable is on the left of the equal sign on the top, and everything else is to the right of the equal sign. To do that, we're going to use algebra, and in particular, a very useful relationship is the crisscross method. So notice that this T2 on the right on the bottom, if we bring that across the equal sign, it's going to go to the top. It goes from the denominator to the numerator. This T, and we want to bring everything else to the right, so this T1 is going to go from the bottom to the top. And this V1 on the left is going to go from the top to the bottom. Okay, so our final equation is going to look like this. T1 will be on the top. Okay, V2 will be on the top divided by V1 on the bottom. Okay, the next step, plug in the numbers. So T1 was 0 degrees Celsius. Now notice that we cannot use Celsius in our equations. We have to use an absolute temperature scale, and that is Kelvin. The conversion is Kelvin temperature in Kelvin equals temperature in Celsius plus 273. If you want to go in the opposite direction, you take Celsius and you just subtract 273 from the temperature in Kelvin. Okay, so I have to add 273 here. And then I take V2, which is the second volume, the final volume, which is 745 milliliters divided by 345 milliliters. Okay, you have your equation. The only thing left to do is to cancel like terms. The milliliters cancel and take out your calculator. So I've got 0 plus 273 equals times 745 equals divided by 345 equals, and that equals 589.5. Where's my 8? Kelvin. Okay, well, what is it in Celsius? Well, to get that, we have to subtract 273. Equals 316 degrees Celsius. Okay, so it makes sense. In order to get this larger volume, you have to expand the gas. And how do you expand the gas? Well, you add temperature. That makes the gas particles go faster. They have more collisions with the interior wall of the container, and the wall is flexible, so it expands it out to a bigger volume. Okay, so good luck on the quiz. See you later.